I hope you can all see me, see my screen and hear me clearly. A very good morning to all of you. If you can hear me clearly, then please let me know by typing, texting. So let's start with the work. We are doing Newton's laws of motion and its application. So last class we did discuss how to apply Newton's laws of motion. We will devote even this class also to take up some of the more examples. Remember Newton's laws of motion. F is equal to here ma, or F is equal to m d2r by dt square. They are equations in three dimensions. So you need to solve them, you need to write them independently and solve them independently. So maybe I can devote one or two more lectures. Newton's laws of motion are supported by two more concepts. One is vectors and other one is kinematical equations. So you need to be thorough with them, which I presume everyone knows. So we have not gone that far back and started. So as I said, we don't plan to take problems which are very elementary. We plan to take problems which are sufficiently challenging. Uh, all of you have done at least one primary course in mechanics in the SEM 1. Physics students have done another course in mechanics in SEM 5. And I'm sure math student also must have done some problem solving in mechanics. That gives us a very good opportunity to look at some of the challenging questions. So let's take the next question. A student suspends a chain consisting of three links, each of mass m equal to 0.250 kg from a light rope. She pulls upward on the rope so that the rope applies an upward force of 9 Newton to the chain. So the tension is given. Draw the free body diagram for the entire chain, considered as a body and one for each of the three links. Use the diagram of part A and Newton's laws to find the acceleration of the chain. The force exerted by the top link on the middle link and the force exerted by the middle link on the bottom link. Treat the rope as massless. So, as I said, all applied physics lectures, sit with your pen and paper. So, if you haven't, please get one and start solving this problem. I give you a few minutes, 2-3 minutes to solve it. 5 minutes, it's not more than a 5 minute problem. So, I just take that time and try to solve it. In the meantime, I will just draw a rough sketch. So get your pen and paper and get into solving. So I have a, say, some sort of rigid support, a ceiling or something like that, to which there has been a rope and there is a chain. Now, chain means it has to have some sort of heavy. This is how the chain is there. Okay, the chain is not hanging, but she is pulling upward. So maybe I don't need this part. It's been pulled upward. So you all know that in general there will be an acceleration upward, and what is given is a force acting in the upward direction, which is given to be 9 Newton. So you can start with the part A. So I am very slow in solving it. People, please go ahead, and if you can solve it, do it. And those who are finding it challenging can work along with me. So it says draw a free body diagram for the entire chain. So we all know that if you have to take entire chain as single body, then the free body diagrams tells you to convert, take the entire chain as one single point mass. So I have a single point mass. Now, if it's a single point mass, what are the forces acting on it? So you know that forces acting on it will be mg downward. So this is my mg. Now what is my mg? Look at it. Now you have three chains. One is 0.25 kg. So three chains together will give you 0.75 kg. Okay. Now that into, I will take gravity for simplicity 10. So 7.75 into 10, which will give you 7.50. So that becomes my mg. So this many Newton is working downward. What is working upward? So tension is working upward, or F, which I have written here. I may prefer to call it T. Normally we use T as the symbol for tension, unless the problem also involves use of time period. If it's a time period, then perhaps T is allotted for time period and F can come back for tension, because tension is actually a force. If a time period is not there in the problem, you can stick with T as tension. So this is given 9.00 Newton. And I can see that the acceleration is upward. So how do you write Newton's law? So we have developed a sign convention, if you remember. Any force acting upward, I mean, there are many ways to write the sign convention. Now you people are mature enough to look at both. Some people use a very standard way. Vectors pointing upward are positive, vectors pointing downward are negative. Acceleration pointing upward positive, downward negative. Similarly, in a horizontal plane, vectors pointing right positive, left negative. Some people prefer a slightly modified version where they say that we will keep acceleration always positive, and that will decide the directions of rest of the vectors. So if acceleration pointing up, as in this problem, then upward is positive and downward is negative. But in some other problem, or had the chain been descending with an acceleration A, then downward would have become positive, upward would have become negative. Either case, you are physically at the same situation. So here 9 working, I'm just writing slightly detailed. So my sigma F, as the Newton's law says, sigma F is T is working upward minus mg is working downward, acceleration is upward. So if you do this, this is cause, remember. Cause of the motion are these two forces. Effect is acceleration. So as I said, Newton's laws is a cause-effect equation. Find out the causes, equate it to the effect. So now we are in a position 9 minus 7.5. So T is 9, M is mg is 7.5. 9 minus 7.5 will give my ma. So the ma is equal to 1.5. Now that gives me the value of a. So the acceleration is 1.5 divided by m. How much is m? Do remember we are talking about all the three links together. So it is 1.5 divided by point, sorry, 0.75. That gives you 2. So the acceleration should be 2 meter per second square. Now, what next? This was the A part solved. Look at the B part. Use the diagram of part A and Newton's laws to find the acceleration we have found. The force exerted by the top link on the middle link and the force exerted by the middle link and the bottom link. So, and we need to draw a free body diagram for the each link. So let me draw the free body diagram for the each link. Let me call the lower link as 1, this link as 2, and this link as 3. So I think for this part I can give you the free body diagram and then you can solve it. So if I look at the lower link, And in that case, lower link will be reduced to a point mass. Okay. Now, if the lower link has, what are the forces acting on the lower link? So you will find that its weight mg will work in the downward direction. So m into g, that will work in the downward direction. This is mass 1. What is the force working here? You can easily see it's two bodies in contact. So whenever there are two bodies in contact, you will get normal reaction working. So the normal reaction will work at this position. I will call this normal reaction as N1. Remember, it's a normal reaction between 1 and 2. So it is customary to write it as 1, 2. Of course, acceleration is upward. Do remember. This I'm not drawing right now here, but the acceleration is upward. So when you write this kind of law, you will write N12 minus mg is equal to ma. Now we go to this one, second link. So all I'm going to do is now on the second link, if you look, what are the forces acting? So its own weight will work downward. So the weight of the second link, which is again mg only, it is nothing different. It will work downward. What will work else downward? So you can see that the two chains are in contact. So there is one normal reaction also working downward. Now remember, this normal reaction is again between 1 and 2, and it's a reaction pair of this. So this would be called N2 1, and do remember that in magnitude it is equal to N1 2. Then what happens here? At the upper section, there's another chain here. So I can draw another reaction force from the upper chain. It is working on 2 by 3. And remember that the acceleration works upward. So when you write the Newton's law, it will be N23 minus mg minus N21 is equal to ma. How does it go for the third link? Again, third link is a point mass first. We have made it. And then this is third. Of course, its weight mg will work downward, which is same in all the cases except in the first where it was actually 3 times mg. What are the other force? So downward link, there is a reaction force. Now, so there will be a reaction force which is called N acting on 3 by 2. But do remember that this is equal to this one. It's a reaction pair. It will be N 2 3. And now there is a tension working upward. So what you have here is tension working upward. Remember that entire system is accelerated upward. It is sometimes the vector diagrams are for acceleration are not mixed with force, they are drawn separately. You can write down your equations. Remember that this is N12 minus Mg will give you Ma. This is my first equation. Second equation will come here. N23 minus Mg is equal to, no, wait, then this one minus N21 is equal to Ma. Then this one. So you have T working in the upward direction minus Mg working in the downward direction minus N32 working in the downward direction is equal to Ma, upward direction. Apart from these are two more equations. One is this one and one is this one. So total you get 5 equations. What is asked is the force exerted by the top link on the middle link. So you have been to calculate N23. So I hope that you can do from here. I leave this from this point onward for you people to solve. You have to calculate N12 and N23, the two normal reactions. So please do that. Okay. So let's take another problem. This is slightly different. We will come to it later. Let me take this one. Two ropes are connected to a steel cable that supports a hanging weight as shown in the figure. So you have this support, you have two steel cables, and you have a block. Draw a free body diagram showing all the forces acting on at the knot. You have to, knot is here. You have to find the forces acting on the knot that connects the two ropes to the steel cable. Based on your force diagram, which of the two rope will have the greater tension? Which one will have greater tension? If the maximum tension either rope can sustain without breaking is 5000 Newton, determine the maximum value of the hanging weight that these ropes can safely support. You can ignore the weights of the rope and the steel cable. So yeah, try to draw its free body diagram. Draw a free body diagram showing all the forces acting on the knot. So take this as a point and figure out what are the forces acting. Many of you have done this kind of experiment in your junior college, by which where you hang two masses over two pulleys and a central mass and do this kind of experiment. So draw a free body diagram of the center point. I give you 2 minutes. Yeah, so try to answer the first question. A free body diagram, how would it look like? So now computer technology gives me some advantages. So let me use those advantages to draw the free body diagram. So all I need is, let me use some different color and try. This is the knot. So I have one force acting tension in this. I may call it as T1. Tension in this cable. Remember, these are different cables. They are not the same cables. So you cannot have same tension in all of them. So this is my T2, and tension in this part of the cable is T3. Now once I have drawn it, the technology gives me an option to remove my figure and retain my free body diagram. Isn't it beautiful? I could not have done this on a blackboard. Now, yeah. So, how do you resolve your forces? So, remember that this is 60 degree and this is 40 degree. This is not 90. It is less than 90. So, T1 and T2, these forces are not orthogonal forces. So, one of the ways to resolve your forces would be along the vertical and along the horizontal. That is how I can resolve. Technology gives me a zooming option as well. So let's use it. Beautiful. So I can remove this T1 written over here, and I can may write T1 here. T2 is proper. Now I can resolve my forces into components. How do I do it? So you are all familiar. Drop a perpendicular, and then this becomes my component over here. Now let me check the forces. Sorry. the angles. This angle is 60, sorry, 40. If this angle is 40, then this is also 40. And this is 60, that means this is also 60. So we can use these facts to take our problem forward. Now this angle is 40, so this component becomes, as you can guess, T1 cos 40. And if you drop a perpendicular here, then this becomes T2 cos 60. Now one first question that is asked to you is, which of the two tensions are greater? So how do you find it out? So you can see that there is no lateral displacement. The system is neither moving, accelerating to the left nor to the right. It is in equilibrium. That means T1 cos 60 has to be equal to T2 cos 60 has to be equal to T1 cos 40. So you can always solve it. You can say T2 cos 60. Cos 60 is 1 by 2, has to be equal to T1 cos 40. So what do you get? You get T2 by 2 is equal to T1, and how much is cos 40? Let me check. If you have an access to your calculator, you can use it. 0.76. 0.76 or point into 0.76. So I can take T2 upon T1 will be 1.5 divided by 1. So which one is greater? Can you tell me? If you look at it carefully, you will find that T2 is greater than T1. Why T2 looks greater than T1? Because T2 is 1 proportional to 1.5, T1 is proportional to 1. So the answer to the first part is T2 is greater than T1. Can you tell me what will be the condition under which they both will be equal? T2 is equal to T1. What will be the condition under which T2 will be equal to T1? So you can see it's straightforward. If you want both of them to be equal, then it has to be 1 here. That means the angles must be same. Avalon, you are correct. So the angles must be same. So just by looking at the angles, you can actually predict whether the tension in the two parts of the rope is same or not. That is the beauty of having some experience in solving the problem. Just from the angles, you can guess, predict. Okay. Now, what are the forces acting upward? So, upward forces acting are, you can easily see, you have T2 sine 6, you will have T2 sine 60, this one, and from this here you will get T1 sine 60. So T3 has to be equal to the sum of the two. So you get T1 sine 60 plus T2 sine 40 equal to T3. But if you draw a free body diagram of this block, only this block, then how would it look like? So for the block, mg is working downward and tension in this cable, which is T3, is working upward. So you get T3, which is the right hand side of this, has to be equal to mg. So this actually solves the second part. If the maximum tension in either cable can sustain without breaking is 5000 newtons. So which cable will break first? That is another question. So you can see that the cable that will break first will be the one which has higher tension. Now we have already seen which one has the higher tension. T2 has the higher tension than T1. So this cable is going to break first. So if this cable breaks first, then you put this value as 5000 Newton. Determine the maximum value of hanging rope. So you can, from using this, you can find out mg. So again, I leave that part for you people to solve. Is now almost done. I have taken one more problem, uh, but let's take it in the next class. This is interesting. Maybe we can stop here.